This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Electric, or the thickness of the structure, why do we have these two formulas, and why do we have to use one over the other? And what's the motivation for that? So that's essentially the motivation, or why there are actually two formulae. But as far as you're concerned, what you would do is you'll do the analysis, work out what the width to the thickness of the dielectric slab is. If it's less than or greater than 0.35, it will tell you which formula you need to use. Then we went through and again we derived, we actually copied, I should say, we didn't derive in this particular case, the loss due to the conductor. And we've got the following formulae. And again, depending on the ratio, of the value of the characteristic impedance multiplied by the relative dielectric constant, if it's if it's less than or greater than 120, we use one of the two formulae, where A and B were given here. And then what we also did was we briefly described what happens when we've got the dielectric constant. Sorry, if we want to work out the loss due to the dielectric, and we rewrote that in terms of the loss tangent of that particular material. And essentially, if you remember, I forgot to bring it today. What we had was I brought up a data sheet and showed to you if you were designing a PCB board, based from a particular manufacturer, what you would look at is, depending on the material that you're using, you would look at the dielectric constant for the frequency or the range of frequencies that you were trying to design your PCB board for, and you would also look at the corresponding loss tangents. And from there, as we showed in the example, you were able to work out not only the thickness and the properties of the dielectric of the conductor that you required, but also what you were able to do is estimate the total loss, which was essentially the loss due to the dielectric and the loss due to the conductor loss. All right? And so what we essentially did was we substituted into the appropriate formulas for AD and AC. AD was just the dielectric loss, and we said that was essentially just K times the loss tangent. The conductor the loss due to the conductor was a much more complex formula, and we had that written down. And that gave us the total loss in nepers per metre for both the dielectric and the conductor loss. And then what we were able to do is work out what the effective loss per metre was. And essentially, since we said, well, we were designing this PCB board to operate at 10 gigahertz, we worked out what the effective wavelength was in that material at 10 gigahertz, right? And then we worked out the equivalent loss per wavelength. And it turned out to be roughly 0.05 dB per wavelength, right? Which generally is pretty good, right? Usually on some chips or other types of structures that you build, especially at higher frequencies, you might be getting 5 to 10 dB per millimetre loss. Okay? All right. Then we went through and said, sometimes we can't build a strip line. Sometimes we want to route to the top of the PCB board or to the bottom. And under those circumstances, we don't have a symmetrical structure. We've actually just got a conductor on top of a ground plane, separated by a dielectric. And we went through the process of showing that in this particular case, or we discussed in this particular case, what happens is that the electric field is not symmetrical, because on the top we've got air, in the bottom we've got a dielectric, and essentially we know that we've got more field lines through the dielectric, because that's essentially what a dielectric does. It actually amplifies the effective electric field. And as a consequence, what we said was, the true propagation on a microstrip is not exactly TEM, right? It's quasi-TEM, But in order for us to be able to do the analysis, and what people have done is that they've come up with a way in which they are able to approximate what is actually happening on that particular structure. And essentially what we went through was go through the process of defining an effective dielectric. And of course, based on the effective dielectric, we determine the phase velocity and the propagation constant. And what I mentioned, or what we derived in our formulae, was that the effective dielectric constant is going to lie somewhere between 1 and the dielectric constant of the material. Okay, why is that the case? Does anyone remember? Did we go through this or not yet? Okay. All right. So essentially, we know that the top is air, the bottom is the dielectric, right? So if you're working at the average, right, the number has to be somewhere between the two, right? Because it's not all, it's not all air and it's not all the dielectric material. So therefore, the number, the effective dielectric constant, is going to be somewhere in between those two. And essentially, what happened is we derived a formula, or we're given a formula which allows us to calculate what the effective dielectric constant is for this particular structure. And essentially, the effective dielectric constant is equal to the relative dielectric constant of the material plus 1. Where does the 1 come from? Yeah, perfect. All right, and we're averaging. And then likewise here, there's also the relative dielectric constant minus 1 divided by 2, and the square root of this function in here, which is written in terms of the thickness of the dielectric slab to the width of the conductor. Now, what I'm going to say, like what we did in strip lines, we're not actually going to derive these equations. You can assume that they're some God-given fact, or essentially what people have done is have gone through the process of actually fitting these functionals to the characteristic impedance versus dielectric constant versus effective dielectric constant versus the height of the dielectric and the width. And they've come up with these two formulae depending if the ratio of the width to the thickness is less than 1 or greater than 1. Okay, so that you've got two formulae that you need to look at depending on whether you have the ratio of the width of the conductor is smaller than the thickness, or if the width of the conductor is actually larger than the thickness of the dielectric slab. Okay. And then what I said was usually usually in most circumstances what you're asked to do is to actually design a strip line or a microstrip of a given characteristic impedance. Usually, sometimes you might want to say, well, given these dimensions, I want to work out what the impedance is. But generally, as a designer, what happens is you say, well, I want to connect these to this source and this load. I want to optimally match it. So therefore, I want to design a transmission line with the following characteristic impedance, right? And what we do under those circumstances is I've given you the methodology, on how to do that. And essentially, what we've got is we determine the width to the thickness of the material. And usually the thickness of the material, for all of you that have seen or designed the PCB board or designed the chip, the thickness of the layers are predefined. Or you may have some flexibility, but you don't have arbitrary flexibility in being able to design the thickness of those layers, of those dielectrics, right? Usually, if you're looking at FR4, for example, you have certain thicknesses of dielectric that you can actually choose from, right? You can't actually go there and say, I want 8.7321 millimetre thick layer of FR4, because the manufacturer is going to say, well, good for you, but these are the only ones that we sell or we produce, right? So therefore, under those circumstances, what you've got available to you, or the only thing that you've got available to you, is to modify the width of the actual conductor. And even then, there are some restrictions, right? So therefore, you just, I don't know if you've actually gone through the process of designing a PCB or a chip, but usually you can only design the metals or the conductors to certain widths and certain thicknesses. The thicknesses are usually predefined, at least on a chip, but on a PCB board you can actually choose the thickness of copper to an extent. There are certain options that you can actually, that you have to your disposal. But generally the width also depends on the resolution of that process. So you can't actually choose arbitrary or design arbitrary widths also, right? So that might mean under certain circumstances, even though you might want 51 ohms or 50 ohms, or you might want 50 ohms, you might get 48 or you might get 52, right? As an example. Anyway, so there we said, like, suppose we wish to determine a microstrip with a particular characteristic impedance. What we do is we use the formulae in order to work out the width to the thickness of the material, where essentially we are given these other two values. We got the width to the thickness of the dielectric material is written in terms of these two formulae, and where A and B are essentially the two values that are defined in these two equations. Okay, and again, just to repeat, I guess it's important to emphasise that these are just formulae that you're given, right? Don't try to derive them. Don't try to think of where's the magic, where's the physics, where's the intuition behind it. There isn't any in this particular case. What people have done is they've just fitted those equations. Okay, so just say, okay, what I've done, someone's given me those two equations, or those set of equations. If I want to design a microstrip, I'm going to use those equations. All right? And for these particular microstrips, and I should have called this a microstrip, I've actually, sorry, that should be microstrip rather than strip line. You've also got the attenuation, right? A formula for dielectric attenuation, and also the conductor loss. Okay. Now let's do an example, which is something that you probably experience the very first time you're designing a PCB board, a high-speed PCB board, right? So usually someone might tell you, design me the cheapest PCB board, which will probably be 2 layers, right, top and bottom, with essentially what I'm saying is a piece of dielectric material in the middle, top and bottom conductor, right? And somebody says to you, well, for argument's sake, we want you to design a microstrip line on a substrate. In this particular case, it's an expensive substrate. It's actually an alumina substrate. Usually, if you're designing something, you'd probably be given FR4 to design with, because that costs roughly 10 cents per square inch, whereas alumina is probably going to cost you $3 to $4 per square inch. Anyway, so somebody might say to you, well, design us a microstrip line on a particular alumina substrate. This substrate has a relative dielectric constant of 9.9, a loss tangent of 0.01, and we want to design something that has a characteristic impedance of 50 ohms. And then they might ask you, well, what we want is a 270 degrees phase delay. Okay? And then they might also ask you, well, for this particular length of line, or, you know, what is the loss that I am expecting? Okay, this is a usual design problem, right? This is a very standard design problem. Now, Can anyone think of a situation where you might want a phase delay? Will? Come on, man. When we're doing the phase delay on the 60 gig chip. Okay, yes. Yes. Yeah, you can do 90 degrees. Now, if you're trying to do 90 degrees that way, that's probably not the best way of doing it because it's very frequent. See, it's only 90 degrees at a particular frequency. But yes, you can do that. Or, for example, if you wanted, in a particular case that I was talking about, Will, is where we're designing chipsets, 60 gigahertz chipsets, and we're doing phased arrays on these chipsets, for VR applications. And you want to be able to have a sequence of antennas and phase the antennas relative to each other, so you can form a very narrow beam in order to do beam forming. You can actually use this technique in order to, switching particular lengths of line in order to get the relative phase change, right? Or as your colleague has just pointed out here, if you want 90 degrees out of phase. So for example, if you were designing your communication systems and you want your sine and your cosine, what you do is you put your sine in one line, and wait for 90, and you have a 90 degrees phase shift, or you put a sufficient length of line, so you get a 90 degrees phase shift on the other end. Okay, so in order to do the design here, we first, as we've gone through our process, is that we need to calculate, and essentially we're making a guess, right? Which was, remember, we had two formulae that we needed to, we needed to calculate A. We go through the process and we calculate this value A, where Z0 is 50 ohms, ER is 9.9, and if we go through this process, we calculate that this value A is actually 2.142. Great. And then in step 2, what we needed to do, if you remember the process, was essentially to calculate W and D. And remember, we said that W and D depended on whether W on D was less than 2 or greater than 2. In this particular case, let's assume that it's less than 2, do the calculation, and then if the answer turns out to be correct, then we'll say, yes, it is. If not, then we'll have to calculate the other, the value using the other formulae. So we go through the process and we find that W on D is 0.9654. Great. Less than 2, we're fine. We don't have to do the other calculation. Okay. Right, so therefore, in this particular case, we now know the ratio of W to D equals 0.9654. We also know the thickness of the material, the thickness of the dielectric slab that was given in the question, right, where we had 0.5, and which means that the required width is 0.9654 multiplied by 0.5. I don't know why I've put 0.55 here anyway, but sorry, I've made a mistake. And then you can calculate the actual width. Okay. Now, the other thing that you would do here normally if you were doing a design is you may not, as I said, be able to, on your particular process, actually get 0.483 millimetres. Right, you might only be able to get 0.48 as an example, or you might be able to get 0.48 or 0.49 as an example. Right, it's because just your design tolerances or the design rule checks or the designs on your particular process. Right, and therefore what you're able to do there under those circumstances is work out what your achievable characteristic impedance is. Right. Now, once we've done that, we can actually work out our phase shift, right? And we know that beta L, which is 2 pi on lambda effective, which is lambda on square root of epsilon, is our effective phase change, right? And we know that 2 pi on L naught, which is what it is just in free air, is equal to 209.4 per metre. So therefore, what we're able to do is resubstitute this value into here, and it tells us in order to achieve a 270 degrees phase shift on this particular dielectric, we need a transmission line, or the length of the transmission line is going to be 8.72 millimetres. Right? So now you've got two things. You know how to determine the characteristic impedance of a particular transmission line, how to actually dimension it for your particular substrate in order to achieve the characteristic impedance that you desire. And then what we've also done is we've worked out a relationship between the length on that particular medium and the resulting phase change. Now, as I said, the last thing that we probably want to do is to actually ascertain or determine the loss on that particular material or on that particular substrate. So what you would do is calculate the total loss, which is, we work out AC plus AD, which is the loss, the propagation constant, or the loss due to the, in the propagation constant loss to the associated to the conductor, and that associated with the dielectric constant of the dielectric. And we'd gone through the process where, you know, again, this is just the formulae written in terms of 2 pi on lambda, which is K naught, ER, and the loss tangent. And if you go through this process, you find that the loss related to the propagation constant is 0.255 nippers per metre. Right, and here what I'm showing you is how to convert from nippers per metre to dB per metre. Right, which is just a very simple formula, which is essentially just 20 times the loss due to nippers per metre, and then divided by log, natural log of 10, which is essentially converting from log base E to log base 10. And it turns out to be the 0.22 dB per centimetre. And of course, here I've also calculated the conductor loss, and I substitute the two, I then add the two, and then calculate the loss per centimetre. So therefore, for 8.72 millimetres, you get an effective loss of 0.1 dB, which, all said and done, is nothing in this particular case. But as I said, this is a very good material with a very low loss tangent. If you're looking at FR4 at 10 gig, it's probably going to be many dB, right, per centimetre. Right? Okay. Exciting? So who thinks they now, if I said to you, design me a transmission line on a PCB board, if I gave you a data sheet and told you design me a transmission line on a PCB, they would be able to do it. Yes, one? Why isn't everyone putting up their hand?
What if it's not a straight line?
What do you mean if it's not a straight line?
I'm not sure if there's like a...
Okay, well, that's interesting, and I'm glad you brought that up. And I'd like you to do something for me, okay? If there's an edge, what I'd like you to do, maybe in the next lecture, just one or 2 minutes, tell me what happens is if I've got this kind of transmission line, or if I've got an edge, what else should I do? Or something like that. Just look at a couple of these structures and tell me what the equivalent model is for those and why. It'll be a lot of fun. Yeah, just look it up. I mean, I'm sure it's in Poser. It's in Poser also, right? But what's interesting is these will add something to this how do you call it, transmission line. This discontinuity or this sharp edge causes some issues, and it'd be worthwhile, educating your friends and your colleagues on what effect that does have, and why, if you're at high frequencies, you don't actually put sharp edges in your transmission lines. You try to make all your transitions as smooth as possible. But notwithstanding that, if I said, well, with no edges, how would you design a transmission line? You should be able to all do it now, right? There shouldn't be any excuses. You should be able to pull up Altium or Cadence or whatever and actually design a transmission line, at least by hand, and have it dimensioned appropriately, so therefore when you do your appropriate simulation, you know roughly what the characteristics of that transmission line are going to be in terms of characteristic impedance, loss, etc., etc., etc. Okay, now on that note, we're going to move on to something even more exciting, and something that I've been told you've done a lot in your workshops, so therefore this should all be very simple revision, all right? Now for everyone's benefit, I'm holding a very dangerous piece of equipment up. Has anyone seen something like this before? Yeah, you haven't? You have. Okay, so it's a compass, right? So who's used a compass before? So everyone? No. I've got at least one person not used a compass. Okay, so in my age and probably Will's vintage, what would happen is if you wanted to draw a circle, you would use this piece of equipment in order to be able to draw a circle. So you'd put, essentially you would determine the radius and put it on a piece of paper and turn it around or spin it around and you draw a circle. Now, what we're going to find is when we're doing Smith charts, essentially we need to be drawing voltage standing wave ratio circles, and in order to be able to do this effectively, I'd suggest that you buy yourselves this dangerous piece of equipment, and I'm calling it dangerous because it's got a little pin at the end, and I'm sure if we were supplying it through the university, we would need to do some kind of occupational health and safety and, you know, playing with pins and things like that. So, you know, just be careful with this very dangerous piece of equipment. Now, what I'll do is talk a little bit about Smith charts. So, you've done Smith charts in your workshops? No. They told me that it was part of the process where you were, not workshop or tutorials, that you were talking about. So you've done it in your tutorials. So you're intimately familiar with Smith charts? No. Okay. All right. So let's go through it. And now, a Smith chart is just a tool, right? And it's a graphical tool which allows us to do some interesting calculations in terms of being able to determine essentially impedances, and also impedances once we connect an impedance to some kind of transmission line. Right, it allows us, remember we had these hyperbolic tangents and these cot functions and the like, and essentially they were, you know, generally they're very difficult to deal with mathematically, they're cumbersome to deal with, whereas what we were able to do, or what people did when, you know, in the 30s and 40s, when people didn't have computers, right? A computer was, you know, this super expensive piece of equipment which was as large as this room and probably had less compute power than your watch, right? So what people had derived was graphical means in order to be able to solve certain problems. And that's all what a Smith chart is, right? It's a graphical representation of impedance, and it allows you to do some interesting calculations graphically, right? Now, I'll have to come clean in the sense that I'm terrible at drawing. And what you'll see is when you see all my pictures, when I'm actually trying to do these Smith charts, you can actually see that it's a bit sloppy, right? I apologise. The only subject I almost came close to failing was engineering, first year engineering drawing, right? So I'm terrible at drawing, right? So I'm just letting you know. So therefore, when you're looking at these things and you're saying, oh, geez, you know, Stan's drawing is absolutely terrible, I apologise a priori. But notwithstanding that, it's you know, Smith charts are an extremely interesting way or an extremely important way of representing impedances. And most importantly, if you're making measurements using a vector network analyzer, in most cases what it does is it draws the impedance on a Smith chart. Okay? Now, with that prelude, what I'll do is I'll go very quickly through the derivation of a Smith chart. And essentially all that's happened in a Smith chart is they've written down the reflection coefficient and they've written it down in terms of these normalized impedance, right, where you've got some Z, you've divided it by some reference impedance that you want to reference everything to, so therefore you rewrite the reflection coefficient as Zn minus 1 on Zn plus 1. Right? That's the magic, that's the insight to the Smith chart, really, recognising that you can write gamma as this. Now, if we substitute, and we know that this Zn, which is the ratio of these two values, if we rewrite it as a real and imaginary component, and we substitute it into the value for this reflection coefficient, what we know is we're going to have a real part and an imaginary part. And let's call the real part U and the imaginary part V. Right? And once we solve for that, what we find is the real part, sorry, U, it can be written as R squared, which is the real component of the impedance, minus 1 on x squared on R squared plus 1 on x squared. And likewise, V is equal to 2x on R plus 1 squared plus x squared, which is the imaginary component. Now, if you rearrange this, right, in order to be able to eliminate x, so what you find is you can rewrite this U as essentially a circle, which is essentially the equation for a circle, which is U minus R on R plus 1 squared plus V squared is equal to 1 plus R plus 1 all squared. This is essentially the definition of a circle. You probably did this in probably first or second year mathematics. And you might have even done this in year 12, right? Where you first learnt about ellipses, right? Now, the other thing that we also know is as R becomes a very large number, this value tends to a point, right? So, and the point that it tends to is essentially, so if we make R 0, so this becomes almost 1, that becomes 0. So therefore we've got a circle essentially centred at 1, 0. Okay. Likewise, if we do the following process in order to, eliminate R, which is the real part, we come up with circles for which are essentially constant reactance circles on this graph. And if you go through the process, you can actually show that these circles are now located at U, V naught, 1 on X. Right? So essentially all it's done is we've now graphically represented or determined ways in which to be able to draw our reflection coefficient in terms of constant resistance circles and constant impedance circles, and worked out where they lie on this new reference that which we've defined. Now, it's great. What's the significance? Well, it allows us to actually now have a very interesting, let me find you this way of being able to represent impedance. Right? And this is a Smith chart for anyone that hasn't seen it before. Right? But we'll use this and I'll go into much greater details. Right? So essentially all we're saying is we've drawn the U circles and the R and the V circles, and the R circles are actually these lines, right, which are lines of constant resistance. So if I was drawing this, let me grab this. These are lines of constant circles of constant resistance, right? And these circles across here are circles of constant either reactance or susceptance. Okay, which is just positive is inductance, negative is capacitance. But anyway, what I'm saying is these are positive or negative imaginary parts, right? Which are essentially, in this particular, in this notation, either your V circles or your U circles, right? That's all I've done. Right. Now, nothing particularly exciting at the moment. You can think of it in the most simplest of ways. All you can think of as, all of a sudden, instead of using Cartesian coordinates, I've now come up with a new coordinate system. That's all I've done. Right? Nothing particularly exciting, nothing particularly anything other than we've got a new coordinate system which we're going to draw our values or represent our values in. Right? But this new coordinate system has some very desirable properties when we're actually adding or, transforming or dealing with impedances. All right? That's all it is. Okay. Now, the other thing that's interesting about the Smith chart is if you drew a circle of constant, if you wanted to work out admittance from impedance, an interesting relationship in Smith charts is that essentially all you're doing is you're flipping or rotating that point by 180 degrees. Right? So therefore, if you had a point on the Smith chart and you wanted to work out what its admittance is from its impedance, all this relationship is saying is all you will do is you just go around the circle of constant radius until you flipped or moved 180 degrees. Okay? So now let's look at this Smith chart again, and what we'll do is we'll go through some examples so therefore you can actually start to internalise and appreciate what a Smith chart is. Now, the other thing that I wanted to point out in this Smith chart is essentially we've gone through and said these are the lines of the circles of constant resistance. We've said that these are the circles of constant susceptance or constant inductance or reactance. What we've also got is, at this particular point, is infinite impedance, zero impedance, right? And the other thing that's interesting about this Smith chart, just give you, I guess, a little bit of a tour of the Smith chart. At this particular point is the value of the characteristic impedance or the reference impedance. Right, so if you were looking relative to 50 ohms and you had something that was 50 ohms, it would be at that particular location. So if you, for example, when we're going through the process of trying to match something, what you'll find is what we're trying to do is get to this point, essentially the origin. Okay, now let's go through a specific example. Okay. And the specific example is, I want to find the input impedance of a transmission line that has a length of lambda innate and is connected to a load impedance of 50 plus j 50 omega. Right? What do I need to do in order to, using the Smith chart, in order to work out what that impedance is? Okay, step number one. Right, so I'm going to provide you with some recipes here. Is, well, we've got the load impedance. We know that the characteristic impedance of a line is 50. So what we're going to do is we're going to normalise, in most cases, relative to the characteristic impedance of a line. So therefore what we're going to get is Z equals ZL divided by Z0, which is 1 plus J. Right? Now, what we do here is, in order to work out what 1 plus J is, we essentially look at our Smith chart and we say, well, let's find the real component is what? 1. So let's look at the circles of R equals 1. And let's find where does it intersect with the circle of 1j, or the imaginary component of 1j. And we see that this is the circle of 1j, this is the circle of r's, this is u, so essentially this is the circles of u, these are the circles of v, and we know that this corresponds, this particular point is 1 real plus 1 imaginary, right? So essentially this is the location of 1 plus 1j on the Smith chart. Now, the next thing that we usually do when we're designing or using these Smith charts is essentially we draw these lines of the constant standing wave ratio. So essentially what I'm saying is you essentially draw a circle centered at the origin, right? And essentially you go to at the origin and you work out the radius and you draw that circle. So this is where the compass becomes very useful, right? So you put your point here and you draw your circle around that point, right? Now, essentially, what that's doing is essentially saying to you, or enabling you to calculate, if you had this particular load impedance and you were connecting it up with a line which had a impedance equal to the characteristic impedance, essentially the input impedance would vary from and you can make this as long as you liked. Essentially what this is telling you is these are all the values of the input impedance that line and that load will at some time manifest. Is that clear? Yes, yes, maybe no. So what I'm saying is I've got a transmission, I've got a load, all right? And all that circle's doing is saying, hey, what happens if my length went from L equals 0, which is the point itself, to L equals, as it's increasing, what's Z in? That's all I'm saying. And essentially all the values of Z in that you will find, or that you would ever see in this particular situation, are represented by the values on that circle. They're all the possible impedances that combination of line, of arbitrary length, and input impedance, would result in. Okay? So I start from 0 here. I start making it larger. Right? I'm going around this circle up here. So I'm going around this circle. As I'm going larger, 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 I'll get the minimum impedance. And then I'll go up, 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 up again. And then I'll get to my maximum impedance. Right? That's what the circle represents. All the values of impedance that you would expect. Okay? And that's the voltage standing wave ratio circle. Right? So essentially what you need to do is essentially grab the point from the origin to the load, draw a circle around it. That's your voltage standing wave ratio circle. And essentially that tells you all the impedances that you're able to achieve with that combination. Now, the other thing that you can do is, if you wanted to work out what the voltage standing wave ratio is, what's the voltage standing wave ratio? We've discussed this. So it's the maximum voltage to the minimum voltage on the line. What you need to do in order to calculate that is essentially calculate the radius of this line, and where you see where it says standing wave ratio. Okay, you work at the radius of this line. You see the circle where it says standing wave ratio? Essentially all you do in order to work out your standing wave ratio is do that, and you say it's 2.5. This is the beauty of a Smith chart, right? Now, what I asked in this particular example is to say, well, what happens when I'm if this line is an eighth of a wavelength, so an eighth of a wavelength is what, 0.125, right? So what I do in order to calculate my impedance is essentially I draw a line from the centre to this point in order to be able to read off this value, and essentially this is telling us how far we are from the generator. Now, if I want to work out, if I add a point L on 8, essentially what I do is I move around in the clockwise direction a distance of L on 8, which in this particular case is, if I start at 0.16, can you see it now? If I start at 0.16 and I want to add 0.125, I have to get to 0.285, so essentially move until I hit 0.285, which is roughly here. And then what I'm able to do is to work out, so again, draw the line from 0.285 to the origin, and the point at which it hits that line intersects that circle of constant voltage standing wave ratio is essentially my effective impedance, my effective input impedance for the load and a 1/8 wavelength transmission line. So in this particular case, if you read it off, what you'll find is essentially the impedance is 2, which is the real bit, right? So we're on this circle of 2, and the susceptance is, in this particular case, I've also realised that I've made a mistake here. It should be -1, right? Because we're below the line. So right. So positive, negative J, right? Sorry, I made a mistake. I should have put, that should be negative J. All right, so therefore your impedance is 100 minus 50 ohms. 100 minus 50 J ohms. Okay, let's do another example. Okay. I mean, Poser just does a couple of very small examples. I'm trying to do a few examples so therefore you can actually understand the process. Again, suppose I started with a load impedance of 50 plus J50. And I said it's connected with a length of transmission L. L is not known at this moment. I'm just trying to say some L. And the line has characteristic impedance of 50 ohms. I want to work out, using the Smith chart, the admittance of a load, the voltage standing wave ratio, the min and max impedance, and the length of transmission line that achieves the mixed min or max impedance. Okay, so remember, step number 1 was we have to normalise to the characteristic impedance. So we go 1 plus J in this particular case. So 1 plus J, let's draw again 1 plus J. Find the point 1 plus J on the Smith chart. Then pull out this magical dangerous instrument, right? And draw your voltage standing wave ratio circle. Right? All right, so essentially here, draw your circle. Now you've got your voltage standing wave ratio circle. If I want to work out admittance, remember we said it's just 180 degrees phase shift. So essentially all I need to do is reflect this point, draw a diameter essentially through that point, through the origin, and to the point where it hits the voltage standing wave ratio circle again is essentially the admittance, because it's just a reflection. So essentially, if I want to work out the admittance of the load, all I do is I look at where it intersects this point at 180 degrees out of phase, which is on the opposite end of the diameter, and what I can say is, well, this is on my head. Sorry, it's a big head. I apologise. It's on the circle 0.5 real, and then on the imaginary it's 0.5. Okay? So that gives us our admittance. Okay, voltage standing wave ratio. We said in order to work out the voltage standing wave ratio, again, a dangerous piece of equipment, or you can actually use a ruler. Essentially work out this radius, go down here, measure it, roughly 2.5 to 1. Gives you a standing wave ratio. Okay, what's the minimum and maximum impedance? Very simple. Okay, if we look at the characteristics, if we look at the voltage standing wave ratio, we look at the point at which it intersects the real axis, and on this location it gives us our maximum impedance. So if we look at this, it's 2.2, 2.4, 2.6 Z, but in this, remember, this is reference to 50 ohms, so 2.6 times 50 is 130 ohms, so that's the maximum impedance. And the minimum impedance is, in this particular case, 0.4. 0.4 times 50 is 20 ohms. So that's our minimum impedance. So that also tells us if we had a load and we were using a particular transmission line, that the impedance is going to vary from, it's going to go through a whole bunch of complex values, but its minimum value is going to be positive 20 real ohms, and its maximum value is going to be positive 130 ohms. Okay, now if we want to work out what the length of transmission line which achieves these values, all we need to do is, again, work out our location, which is work out what the length of line is. So we start at this location, we're moving towards the generator, and you work out essentially what the difference between 0.25 and this value, which I believe is 0.16. So it's roughly 0.09 of a wavelength. So if you add 0.09 of a wavelength of transmission line to this load, you will achieve the maximum impedance, right? And likewise, if we want to work out the minimum impedance, we have to go all the way here. So you have to, essentially that is we said that's 0.9, and this is a quarter of a wavelength, so it's 0.34 of a wavelength. That gives us our minimum impedance, right? So as you can see, it starts getting really interesting. A Smith chart starts giving you a lot of information, and you can do it very easily using these graphical means in order to be able to do that. Now, I've still got a couple more minutes, so I'll actually go a little bit further if you guys allow me to. So, you know, we've worked out the voltage standing wave ratio, we've worked out where the Z min and Z max points are, and we also worked out from the Smith charts where the maximum impedance and the minimum impedance occurs, right? But remember, the maximum and minimum impedance always occur on the real, when ZR is, sorry, when the impedance is real, but the length depends on what the initial impedance is, right? So don't just think of it, it's not always 0.9, depends on where you are, where you start off from, right? Okay, one last example, and I've got 2 minutes. This might be a little bit tough, but I'll go very quickly through it, and we'll go through it in the next lecture. So essentially, I've got a 50 ohm transmission line. It's terminated with a particular load, and I'm going to add to this a shunt at a distance, a shunt stub at a distance of 0.04 wavelength from the load. And this actual stub has a length of 0.147. So what am I doing specifically? Where's the pen quickly? I had a pen, I promise. Okay, let me steal this. So what I'm asking you to do in this particular example is the following. So we've got a load, and I'm saying we've got a transmission line which is 0.04